My name is Abigail Graese. I'm an undergrad at the University of Colorado at Colorado Springs. I'm giving you this presentation today from Colorado. We tried all night to get to the conference, but unfortunately our flight was canceled and we couldn't get out on another flight. So I'll be talking to you about assessing the threat of adversarial examples against deep neural networks from Colorado. So deep learning has made significant progress in several different applications recently, such as text and speech recognition, pattern recognition, and computer vision. And as we've continued to do research into deep neural networks, we discovered these things called adversarial examples. So adversarial examples are images can be generated which cause a misclassification by the deep neural network, but which are also imperceptibly changed from the original image. So for example, in our top left corner here, we have a 0 on the top, and then what looks to be a 0 on the bottom would be classified as a 5 by the deep neural network. And these adversarial examples are generated by adding perturbations to the image. For example, you can also make look like an airplane, or flip an attribute from young to old, for example, as we have in our lower right here. And in the middle, you can see the noise that was generated to flip the attribute. And in this image, it is magnified by a factor of 25%, just so that you can see what the perturbations kind of look like. A couple different ways of generating these adversarial examples. The first of which is the fast gradient sign method, which is, and the adversarial examples are generated by adding perturbations using the sign of the gradient of loss with respect to the input. So you can see the perturbations that are generated by the FGS method in our lower three examples here. So kind of the gray values that you can see all throughout the image are the perturbations that are added to our adversarial, form our adversarial example. But even though you would classify the 0, 1, or 2 as such, the deep neural network would misclassify them as a different number. So that's kind of what the deep neural network sees from the adversarial example. And the second method of grading adversarial example builds off of the fast gradient sign method that uses a scaled version of the gradient of loss. And in these FGV images, you see that the perturbations are much quieter and much localized to the object in the image. So the perturbations that are added are these gray spots here and kind of more around the image itself. And then even though your eye would classify these images as a 0, 1, or 2, the deep network would not classify it as such. As we think about the applications that deep neural networks could have in the future, what if we used a deep neural network to classify checks? So if you could an adversarial example onto the check, make the handwritten digit an adversarial example. So then you could classify a 1 as a 9 or a 9 as a 1. So an adversary could take more count than you originally intended. So when we are thinking about our image acquisition process in the real world, how we're going to get images into the deep neural network, remember that there are always going to be imperfections. So if we're going to get a perfect capture, you're always going to be moving your hand a little bit. When you take the picture, get a little bit of blur. You're going to have some alignment issues. And if we think about the check application, you don't get the check right in that box correctly. You've got a little bit of an alignment issue. Also, ability for misrepresentation of size. A lot of images have to go through pre-processing before they can be part of the data set. And then that we're using our experimentation is the MNIST set of handwritten digits. And this test set or data set goes through binarization before they can be put into the deep neural network. I'm going be ways to combat these imperfections. So there was a paper published by Google in July that used QR codes to help with the alignment issues, and then also printed out blown up versions of the image so that when they captured it, they were able to use the QR codes to help get perfect alignment and also shrink the image down to what the deep neural network was expecting, and that kind of combated any blur that might have been requiring the image acquisition process. When we did our experimentation, we did not use any of these use any of these techniques to combat the imperfections. We want to kind of keep it as real to what could be done in the physical world image acquisition process. So we have a clean image here, and we applied several different transformations to it and to all of the images in our test sets. So our first transformation is translation. So it is worth noting that even though it's hard to see any of the changes that are made in our transformations, they were still generated. It doesn't have to be a big transformation in order for it to make it a deep neural network. So even though you might wouldn't think that moving the one column to the right for our translation wouldn't have a big difference for us, it could have for the deep neural network. So we also added a bit of noise to our image using an OpenCV function. We added blur, which is actually one of the more visible changes. The bright whites are a little bit duller when we add the blur to the image. We also do a crop and resize. This again is kind of representing our misrepresentation of size. So this is also, again, one of our more visually easy to see translations. So you can see the two bottoms that are no longer there. Then we apply a combination of transformations kind of to get the whole pipeline into the deep neural network, because you're not going to just have one transformation when you have the image input to the deep neural network. And I wanted to give an example of our pre-processing technique of binarization. So that just gets rid of any gray values within the image itself. For our experiments, we ran tests on two different LayNet networks. One was raw, which was regularly trained, and then the one was tuned, which is the regularly trained network, which was fine-tuned on a set of 120,000 trained images. So the first 60,000 images were the normal MNIST training data set, and then the second 60,000 images were those same images, but with a combination transformation applied to them. And for our test sets, we used the normal set of 10,000 MNIST test images, and then we used a set of 10,000 FGS adversarial examples and a set of 10,000 FGV adversarial examples as well. So these are the results. I'll give you kind of an explanation of what the graphs do. The first two columns are on the MNIST test set, and the second two columns are on our FGS test set, and the third two columns are on the FGV test set. And then we fine-tuned is abbreviated as FT, so that is the performance on our fine-tuned network. But with no transformation, you can see 100% of the FGS, FGV adversarial examples were classified incorrectly. We did the fine-tuning, we got rid of almost 60% of those adversarial examples already. And when we applied the translation transformation, we got rid of between 65 and 75% of adversarial examples but on our raw tuned network. And we applied our noise. We got a little bit worse performance here, only about 60% for fine-tuned, and then FGV on the raw and fine-tuned. We have a little bit of a worse performance for our FGS on the raw network, but that contributed to the fact that the perturbations for FGS images are already very easy. Adding more noise does not necessarily combat the adversarial nature of the image. So it doesn't perform as well as the SV or the FGS on the fine-tuned as well. Added blur to the image. It again got rid of between 60 and 65% of adversarial examples. In resize, it got a little bit higher performance, between 75 and 80% of adversarial examples. And again, the resize transformation was to mimic the misrepresentation of size that could be acquired in the image acquisition process. Of transformations applied, we achieved a performance between 70 and 85% correct classifications by the deep neural network on our adversarial examples. We did run experiments with 5 crops. So the thing is using crops, a technique that's used in a lot of other deep neural networks. For example, GoogleNet uses 144 crops. AleXNet uses 10 crops. So this is a technique to increase accuracy by the deep neural network. So for our 5 crops, we have 4 corner crops and a center crop. I achieved real performance for this between 70 and 80% for our FS and FGV adversarial examples, and even higher for our FGS on our raw network. With binarization, we achieved performance close to that of the network on clean images, both on raw and fine-tuned test sets. Back to the purpose of what we're trying to achieve here is assessing the threat of adversarial examples on deep neural network. And thinking about this threat for written digits, this experimentation has proved that it's not a significant threat. When the images are too small, the pre-processing technique takes care of the majority of deep neural networks, or adversarial examples' effect on deep neural networks. It allows for correct classification. Some initial experiments on a different neural network. So we did FGS adversarial examples with the combination transformation applied for ImageNet. And so we achieved similar performance as we did for the other transformations. Apply this intuition to autonomous cars, for example. You'll have input coming in from a video camera. You'll have approximately 30 frames a second, and then the deep neural network would have to have over 50% of these inputs classified incorrectly in order for the adversarial example to survive the image acquisition process. And a million chances of this happening. That's only an initial experiment, so future work should focus on how adversarial examples affect neural networks with different stats that cannot necessarily take advantage of the binarization pre-processing technique. So thank you for your time. If you have any questions, I would be happy to answer them if you email me. So thank you